Good morning everyone, this is Abishek Sharma, BSc 3rd semester, Namchi Government College, bearing roll number 19 NS0091. So first and foremost, I would like to thank Sikkim University and Namchi Government College for providing us this platform. And also I would like to extend my humble gratitude to our sir Dr. C.P. Khatiwara for helping me to complete this assignment. So in this video, I'll be talking about parallel theorem for moment of inertia, which is my topic. So before we know about what exactly is parallel theorem for moment of inertia, let us know what is moment of inertia. So it is a quantity expressing a body's tendency to resist the angular acceleration, which is the sum of products of the mass of each particle in the body with the square of distance from the axis of rotation. So in simpler terms we can say like the moment of inertia is equals to L by omega, where I is the moment of inertia, L is the angular momentum, and omega is the angular velocity. So let's move to our main topic, parallel theorem for moment of inertia, also known as Huygens-Steiner theorem, named after Sir Christian Huygens and Sir Jacob Steiner. This is also known as Steiner's theorem only. So now let us find the moment of inertia. For that, let us take a system of particles and we want to rotate this to an axis, about an axis in this direction. So what is the moment of inertia of the body about this rotation of axis we need to find out. So first we need to check that this axis is not passing through the center of mass. For that, let us take an axis passing through center of mass, this axis, and let's just name this as ICM, moment of inertia of center of mass. So here there should be some given properties. For instance, we must know the moment of inertia of axis passing through center of mass and the distance between these two axes. Let us name this A and this axis as ZZ axis. Now this information should be available with us to find our moment of inertia. So we also know the mass of this particle. Let us just name this as M. And now this is the axis of rotation, means the whole body is rotating around this axis. Okay, see, this is the center of mass, and when it rotates it has certain moment of inertia. So now I want to rotate this body about this axis. Now what is the moment of inertia? Let's just find out. There are two axes which are parallel. We make it parallel. Suppose in this body of particle, this is the body of particle, and here is the mass, and an axis is passing through the center of mass, and we want to rotate it about this axis. The whole body is rotating and it gives an additional moment of inertia. Now when I rotate this about this axis, it gives two types of rotation. Like first this is in the right, and now when I rotate this, it comes to the left. So the whole mass of the body is rotating about this axis. So the moment of inertia is I z, this axis, is equals to I cm, moment of inertia of this axis, and plus, and the whole body, the whole mass is rotating about this axis, means this center of mass makes a circle around this axis. So the radius is a square. So this is the moment of inertia of this axis, zz axis, and this is the parallel theorem for moment of inertia. That's all. Now let's look at the proof of this parallel theorem of moment of inertia. Let us take a particle with mass m and distance from the center of mass is r, and the total distance from the axis of rotation is a plus r. So the moment of inertia becomes m a plus r whole square. This becomes I equals to m a square plus m r square plus 2m r. This is for one particle, and for some of all the particles we have I z equals to sigma m a square plus sigma m r square plus sigma 2m r. Here sigma m is the total mass, and this becomes m. Here a is constant, so this is m a square plus sigma m r square is moment of inertia about center of mass. And here from perpendicular axis theorem we know that for all the system I equals to sigma I1 I2 plus b. For whole system the distance becomes 0, so this becomes 0, so we don't write it. So I z equals to m a square plus I cm. Now this is the parallel axis theorem, but more important its application. Now let us take a disc, and here is the center of mass m, and I want to pass an axis tangent to it, and this whole disc rotate about this axis, and the distance is r, or radius is r. Now what should we do to find the moment of inertia? We should apply parallel theorem axis, and we need to pass an axis through center of mass. Let's name this as ZZ axis, this as ICM. Now what is the moment of inertia? IZZ equals to ICM plus mr square. Now for perpendicular axis theorem we can write this as 1 by 4 mr square ICM plus this mr square as it is. Now 5 by 4 mr square. Now this is the moment of inertia of this disc rotating about this ZZ axis. Again Now again, let us take a rod which has mass m, length L, and I want to rotate it about this ZZ axis. And where is the center of mass? Here. We write it here, and we apply parallel axis theorem to find the moment of inertia. This is ICM, and now let's write IZZ equals to ICM plus MA square. Now what is this length? This length is, the whole length is L, so this becomes L by 2. The L by 2. Now as we know, for a rod with mass m, length L, and the distance between two axes L by 2, we have IZZ equals to, we can write as ml square by 12 plus ml square by 4. Here A equals to L by 2, and we square this here, L by 2 by 4, this square becomes ml square by 4. Now we take LCM, ml square plus it becomes ml square 1 plus 3 by 12. It becomes 4 ml square, we can write 12 free. So the total moment of inertia of this rod becomes IZZ equals to 1 by 3 ml square. So the total moment of inertia of this rod is 1/3 of ml square. So this is the parallel axis theorem. So these are the applications of parallel axis theorem. So once again, what is moment of inertia? Once again, it is the opposition to the change in position. If we rotate a body, it opposes. It will oppose. Of course, it will oppose, and the opposition more or less depends upon the moment of inertia. Thank you.